Good morning. Today we will start a new topic which is the statistical thermodynamics. So, statistical thermodynamics is actually the bridge, you can say, between the micro states that we had been dealing with so far in the last so many classes, okay, where we understand that in quantum mechanics, okay, depending on whether you are looking at a simple particle in a quantum well or a potential constraint, or you are talking about electrons in a real crystal structure. So, you have several quantum states which are also called as micro states. So, when I say micro states, these are corresponding to the discontinuous wave vector. Okay. So, they can either be something like the n pi by d kind of quantization, where you put a particle in a potential energy constraint and get this, or it can be in a real crystal where your k can be 2 pi n by L. So, nevertheless what it means is you are having discontinuous values of k, which gives rise to discontinuous values of energy. So, these are called micro states. Okay. So, you have so many micro states, and these are possible states where you can fill electrons, correct. And now in the macro scale picture, in the continuum picture, so you have one big macro state. And what are the macro states that we are concerned with? For example, internal energy, right. As a consequence, you will have temperature. So, therefore, now we have to somehow link this information on so many micro states, okay, and we have to arrive at a way of clearly defining the macro state or macro scale property for the system with so many number of micro states. So, this is where the role of statistical thermodynamics comes into picture. So, we are actually building what we call a bottoms up approach. We are now starting from the fundamental building blocks of individual energy carriers, looking at the discrete nature of the energy states, and now from there we are trying to go to the continuum picture and trying to represent these micro states with some macro scale variables. Then how do we do that? So, statistical thermodynamics, we cannot simply fill electrons the way we want or fill phonons the way we want. Okay, there is a certain way that these electrons or phonons can occupy these energy states, okay, and these are represented by the distribution functions, right. So, therefore, we have to respect the nature of these energy carriers and how they are supposed to occupy these energy states. Okay. So, unless we do that, we cannot simply assume the electrons and phonons to fill the micro states in a the manner that we want to do. So, therefore, statistical thermodynamics does two things. One, it gives you the order in which these states are filled by the energy carriers, number one. Number two, then how do we transfer all these information from the micro scale to the macro scale. Okay. So, eventually that is what we will do. So, therefore, the first part is therefore to look at the distribution of energy carriers. So, we have to understand. So, it is like some builder has built a certain apartment complex, say 100 apartments within the complex, okay, each different size, different requirements, some 1 BHK, 1 2 BHK, some 3 BHK, and we do not know how people will fit in these apartments. Okay. Somebody may prefer a 1 BHK, somebody a 2 BHK. So, that is basically the distribution function. And then finally, when you have find the right people who can fit in this particular house, so then you have known exactly how these apartments can be filled, and this filled apartment now can be used to describe what we call the macro scale, the aggregate of all these. Okay. But to fill this, we have to look at all the micro states, that is each and every apartment, what kind of people can fit in this particular apartment and so on. Okay. So, this is exactly how at the small scales the energy carriers also prefer to occupy certain energy states, and these are given by these distribution functions. Okay. So, to quickly I am sure many of you already took courses on probability and statistics. So, I am just going to directly go into the heart of the matter, and I will just assume that you know how to calculate the probability distribution function and so on. Okay. Now, the question will be, now for example, let us take 3 distinguishable particles. So, I am just giving an example. We have 3 distinguishable particles, and you have 4 energy states or 4 microstates. Okay. So, let us say you have epsilon naught is a ground state, you have epsilon 1, epsilon 2 and epsilon 3. Okay. And now I am going to represent 3 scenarios how these 3 distinguishable particles can possibly occupy these energy states. These are just examples. Okay. So, in scenario A, so you have all the 3 particles occupying epsilon 1 like this. Okay. The other states are completely vacant. Okay. And you can have a second scenario where 2 particles are occupying epsilon naught and the third particle is occupying the highest state epsilon 3. Okay. So, how can you represent that? So, the middle 2 are completely vacant. So, if 2 particles are occupying the lowest one, so they can occupy something like this, the middle and the end of this energy state, and you can have one particle which is like this. This is one combination. The other combination is you can have one on this end, one on this end, these 2 are vacant, and here you can have the third particle occupying the middle. Okay. So, you have another possibility where you can have these 2 occupying the left and the middle and the third particle occupying the right end. So, therefore, when you have 2 particles occupying epsilon naught, one particle occupying epsilon 3, so how many possibilities are there? So, you have 3 possible combinations. Okay. So, if you are having only all the 3 distinguishable particles occupying only one energy level together, so that means only one combination is possible. Now, you can go further and you can say you have one particle occupying epsilon naught, second occupying epsilon 1, third occupying epsilon 2. So, in that case, how many different combinations are possible? So, you can have a scenario C, okay. So, in which the highest energy state is not occupied, for example. So, the lower 3 ones. So, you can have combination where one is occupying the left end here, the other is in the middle, the third one is like this. So, like this you can represent more states. Can all of you do that? One here, the other can be here, the other can be here, right. So, how many such combinations are possible? So, you can first draw and check for yourself. So, you have one here, one here, one here, then you have one here. So, you freeze these two positions, you move this. 27. So, let us draw all of them. So, then you can have one here, in the middle, one towards this and one towards this. So, you should have one in the center now and one in the right, one towards the left. So, if you want to calculate the probability, so therefore, you can 1, 2, 3, 4, 5, 6. Now, let us see how we can calculate the number of states or the number of arrangements possible. So, in case of scenario A, so the number of arrangements okay, this is in the microstates. So, what we call as quantum states. So, these are representing the quantum states and you want to distribute particles into these quantum states. So, the number of arrangements possible in scenario A is given by, so you have 3 particles, therefore 3 factorial, right, divided by, in the first energy level you have 0 particles. So, 0 factorial, second energy level you have 3 particles, third energy level you have 0 and fourth energy level 0. So, the general distribution is that you have n factorial divided by n 1 factorial, n 2 factorial and so on, right. So, this gives you the distribution or number of arrangements totally that are possible for each scenario. So, in this case therefore, how many number of arrangements are possible? 3 factorial by, so you have 1. So, this is what is given by this particular arrangement. So, all 3 basically occupying only one state, one microstate. So, that means you can put them in only just one way. So, now if you apply this to the second case, so you have 3 factorial divided by the number of particles occupying the first level 2 factorial, second level 0, third level 0, fourth level 1. So, therefore, this will be 3. So, you have therefore one microstate here what we call, and these are 3 microstates possible. So, that means there are 3 possible combinations of these filling. Okay. So, similarly, if you extend it to the third scenario, so you have 3 factorial by 1 factorial, 1 factorial, 1 factorial and 0 factorial. So, therefore, how many arrangements? 6. Okay. So, now this is giving you the probability, right. So, therefore, usually what happens is the arrangements will always go towards the scenario of maximum probability. The maximum probable distribution will be the most likely distribution. Okay. So, therefore, the most probable distribution what you are talking about should correspond to the largest value of omega. Okay. So, that means we have to find the possible value of omega which is highest, that will give you the most probable distribution, because the more number of states that you have, more likely that this will be the states occupied by these particles. Okay. So, these are actually not constrained like the way we are constraining in scenario A, B, C. So, they try to occupy as freely as possible. So, that means you have to find the most probable distribution that corresponds to the largest value of omega. So, this is basically the starting point of deriving these statistical distributions. Okay. So, what we will do first is just use the generic formula. So, in general, if you have therefore n number of particles and you have n subscript I particles in each energy state corresponding to the energy state epsilon I, right. So, this is the more generic one. So, therefore, the probability for this distribution will be n factorial divided by n naught factorial, n1 factorial, n2 factorial till what we call n subscript r factorial. So, this r will be the maximum number of energy levels. So, there are totally r energy levels, okay, and you have a distribution n naught may be occupying the base level, n1, n2, n3 so on till the final energy level, and you have totally n number of these particles. Okay, for any given scenario, therefore, you can calculate the number of states, microstates possible using this particular probability distribution. So, this can be also written as n factorial by product n I factorial ranging from I equal to 0 to r. So, this symbol is mean product. Okay. And now, what we will do is we have to find the most probable distribution. Okay. So, the most probable distribution is found out by maximizing omega. So, corresponding occupancy will be determined. Okay. So, now what we will do is take log, natural log on both sides. So, you will have ln of n factorial minus ln of 0 to r n I factorial. Okay. And since typically we are talking about, I mean in a real case these particles are so large, you are talking about so many number of electrons and phonons, they are typically quite large, and therefore, for large numbers of ni's, okay, you can use the Stirling's approximation, which states that your ln of some x factorial is equal to x ln x minus x. So, this is the Stirling's approximation for large values of x. So, typically these particles are also too many. So, therefore, we can apply the Stirling's approximation. So, if you do that and you substitute into, let us say this is equation 1, you have ln omega is equal to n ln n minus n. So, I applied Stirling's approximation to this, and similarly you can also apply the Stirling's approximation, you can expand this and you can apply the Stirling's approximation. How will you expand this? So, this is nothing but ln of n naught plus ln of n 1 plus ln of n 2 and so on. So, and then you apply that. So, you can actually write this as summation I equal to 0 to r ni ln of ni minus ni. Is that okay? So, this will be equation number 2. So, now there is a constraint on the system. Now, suppose you assume that this is a closed system consisting of n particles, and you have several of these microstates, and these particles are now according to these combinations they are occupying the energy states. They can occupy all these energy states under with following constraints. Number 1, the total number of particles cannot change. Okay. So, therefore, your n will be equal to a constant. You can do all these combinations, but you cannot alter the total number of particles. Okay. So, that means your n naught plus n 1 plus still n r should sum up to always n, whatever combination you make, or in other words summation I equal to 0 to r n I should be equal to n, which will be equal to a constant. Okay. Therefore, the change in n, which is equal to summation I equal to 0 to r. So, we can say that, so the change in n should be equal to 0 overall for the entire system. Okay. And similarly, if you look at the total system, the total internal energy should also be equal to a constant. So, if you are assuming this is a closed system, so that means it is not transferring any energy to and from the surroundings, the total internal energy has to be a constant. So, these particles can occupy any energy states, but it should also satisfy this constraint. So, in such a case you will have n naught epsilon naught plus n naught n 1 epsilon 1 and so on till you have n r epsilon r. Okay. So, this gives you basically the energy for a particular microstate, number of particles occupying this particular energy level. So, like that if you sum all of them, you get the total internal energy. So, also the condition now states, so therefore, this is equal to summation I equal to 0 to r n r n I epsilon I. So, this condition states that, so any interchange of particles can happen which conform to the fact that delta u is equal to 0. So, this also means we can write this as summation I equal to 0 to r delta n I equal to 0, right, because of the fact that the total number of particles cannot change. So, you can basically rearrange the particles within a given energy level, okay, but the total number of particles cannot change, and also the at each and every energy level, you can have a certain change in the number of particles, but when they all sum these changes, it should be equal to 0. Same way with this we can write it as I epsilon I delta n I should be equal to 0 because of the fact that the internal energy cannot change. So, let us call this as constraints 3 and 4. So, if you are now going to find out the distribution which is most probable distribution, that is trying to maximize omega, that means even if you interchange some particles among the energy levels, okay, that is you are allowing some delta Ni, the value of omega should not change much, because it is already close to the maximum probability, right. So, you are looking at maximum probable distribution, and you are also looking at the corresponding distribution of n at each energy level. So, even amongst the energy levels you change, so 2 particles here, 1 particle there, and then you rearrange it, that should not change the value of omega too much, because this is already close to the maximum. So, therefore, we can make an assumption that when we are looking at the maximum probable distribution, even some small rearrangement should not affect your overall omega. Therefore, your delta ln of omega should be what? 0. So, already you are going to the maxima, right. So, the condition that therefore, that will ensure is that around this maxima your change will be negligible. So, we can therefore find the maxima by equating this to 0, and therefore, what it means from equation number 2. So, if you therefore apply delta of this to equation number 2, and all of you please write it, find delta of this entire equation. So, we are now maximizing the value of omega to find the most probable distribution. So, if you take the delta of this entire equation, now what you will get on the right hand side, first term you will have delta n into ln of n, correct. So, now delta n should be what? 0. So, similarly you have delta n here. So, you have the first term on the right hand side going completely to 0. So, all of you please try it, and I will just write the solution, you check it later on. Is that okay? So, the second term on the right hand side, the delta of this will expand to this. Okay. So, you have delta of Ni ln of Ni. So, basically you can write this as delta Ni ln of Ni plus you have Ni into delta ln of Ni. So, if you differentiate ln of Ni, that is basically dNi by Ni minus delta Ni. So, therefore, again if you are applying this constraint where the number of particles, total number of particles cannot change, that means summation of delta Ni should be equal to 0. So, what happens? So, this term I mean the summation of that are going to 0, right. So, therefore, essentially you are left with the fact that summation delta n I ln of n I should be equal to 0. So, this should give you the arrangements or distribution of particles which maximizes the probability omega, and which also satisfies the condition that the total number of particles cannot change during this rearrangement. So, from this we will introduce the concept of Lagrange multipliers. Okay. So, the Lagrange multipliers, what we will introduce here so one we will introduce for the energy. So, we will introduce a constant which is having the units of reciprocal energy. So, we will apply this to our equation number 4, which is the constraint epsilon I summation of epsilon I delta n I equal to 0. So, what we will do is we will multiply this by the Lagrange multiplier beta, such that summation you have beta epsilon I delta n I equal to 0. So, this is just a constant. So, we can carry it inside the summation and we can simply multiply it to equation 3. So, this now let us call this as no, let us, do we have a 4? Yes, we have a 4. So, we are multiplying it to equation number 4. So, let us call this as 5 now and 6. Similarly, we will introduce another Lagrange multiplier alpha, so that we will multiply equation number 3. So, we have alpha into delta n I equal to 0. So, this is equation number 7. So, this has this is just a constant, no units. So, you do not have to worry about why we are doing this, but later on we will see that for certain particles or a certain system, these Lagrange multipliers can take certain parameters. So, we will just introduce that later on, but you can now assume. So, we are multiplying equation number 4 with the Lagrange multiplier, which is 1 over the units of energy, and the other one with equation number 3, which is just a constant without any dimensions. So, we have therefore 5, 6, 7, we will add all these together, adding 5, 6 and 7. Summation I equal to 0 to r, we have ln of n I plus alpha plus beta epsilon I. So, your delta n I is common. So, I am pulling this out. So, this should be equal to 0. Is that okay? So, now if you expand this, what it means, you have for example ln of n naught plus alpha plus beta epsilon naught delta n naught plus you have ln of n 1 plus alpha plus beta epsilon 1 delta n 1 and so on and so forth. This all summed to be should be equal to 0. And now as we can see that your delta n naught delta n 1 by itself cannot be 0, because you have a certain change in the distribution. Okay. The sum of all these can be equal to 0, sum of delta n I can be equal to 0, but individually delta n 0, delta n 1, delta n 2, they are not 0. So, therefore, in order to satisfy this, what should be the condition? So, each of these should be equal to 0. So, therefore, ln of Ni plus alpha plus beta epsilon I individually should be equal to 0. Okay. So, from this we can write now what is the distribution, the actual distribution which maximizes omega. So, this is the distribution which is 1 by exponential alpha exponential beta epsilon I. Is that okay? So, this is nothing but exponential minus alpha plus beta epsilon I. So, this gives you the how the particles can be distributed at each energy level epsilon I, corresponding to maximizing omega, corresponding to satisfying the constraints that n should be constant and your u should also be constant. So, this is the most probable distribution, most probable distribution of particles that maximizes omega. Is it clear? So, till here whatever we did was purely statistics, probability and statistics. So far we have not really identified what kind of particles these are, okay. But now what it tells is there is an exponential distribution of the particles. So, starting from the lowest energy level upwards. So, as and when your epsilon keeps increasing, what happens to the number density? Decreases. So, more particles will occupy the lower energy states and then they will taper off as you go to the higher energy states. So, how do we now apply this to particular particle, whether they are electrons or phonons or photons or molecules? So, that is determined by the Lagrange multipliers alpha and beta. Okay. So, I am going to introduce some quick terminology here, let us not spend too much time investigating them, but I am going to therefore introduce three kinds of systems. One is called microcanonical system, microcanonical ensemble. We will see what is this. This ensemble is nothing but a statistical agglomeration of these distribution functions. Okay. So, we can use these ensembles to define the macroscale properties. So, we can have three different kinds of systems, one is a microcanonical one, the other is a canonical ensemble. So, these are just terminologies. The other is called the grand canonical ensemble. So, in this case the question is what kind of particles fit where. For example, in the microcanonical ensemble the probability will be or the distribution will be of equal probability. So, it is just given as 1 over omega. Now, this is a very simplistic approach, okay. And in this case this is applied to an isolated system in which your internal energy is a constant, your volume is a constant and the number of particles are constants. So, these are all fixed. Right. Now, there is one more step I want to do. Now, let us call this as equation number 8, this number distribution here. From this, how can I calculate the probability distribution function? So, I have the number distribution 8. So, from this, how can I calculate probability distribution function, that is P corresponding to a particular energy? Ni divided by so this will give the probability distribution function, right. So, in the case of microcanonical ensemble, it says that the probability to distribute particles is very simple. It is equally probable that all energy states can be filled, okay. Whereas in canonical ensemble and grand canonical ensemble, it goes by the maximizing omega. So, whatever we have derived here as equation 8, so your P therefore follows from equation 8. So, both here as well as the grand canonical ensemble. So, what kind of systems therefore canonical ensemble can be applied? So, you have system where volume is a constant, the number of particles is fixed, and it is also isothermal. So, temperature is also constant. So, these are all fixed. So, typically this is a closed system, therefore, your volume is fixed, number of particles is fixed, and temperature is also fixed. Now, the difference between canonical and grand canonical is that this becomes an open system. So, therefore, your n will no longer be constant. So, your volume will be constant, but what we instead of n we call what is called chemical potential. Mu will be a constant, and if this is isothermal, you can also have T fixed. Okay. Now, as a consequence, how do you differentiate the canonical and grand canonical? In both cases, you use this particular equation to calculate the probability distribution. However, the values of the Lagrange multipliers will become different. For example, in the case of canonical ensemble, the value of alpha will be equal to 0, beta will be equal to 1 by kb t, whereas the grand canonical, your alpha will be minus the chemical potential mu Ni by kb t, and beta will be still 1 by kb t. Okay. So, this is to summarize the different kinds of systems now for which we can extend our distribution function and apply the values of alpha and beta according to the kind of systems we are dealing with. So, therefore, if you write the distribution function in terms of probability distribution, so for a canonical ensemble, your P probability will be exponential minus Ei by kbt, because alpha is 0. Okay. So, if you therefore substitute into this becomes 1, you have exponential minus 1 by kbt into Ei. So, therefore, divided by summation of e power minus Ei by kbt, so I going from 0 to r. For grand canonical ensemble, your probability will be what? Substitute the alpha and beta. What do you get? E power minus EI minus mu Ni by kBt divided by summation e to the power minus EI nu Ni by kBt. So, we will apply the canonical ensemble to system of molecules, phonons and photons, while the grand canonical ensemble is applied to system of electrons. So, therefore, we have now come to a point where we understand what is the distribution function, and second thing, we have also identified what kind of particles correspond to what kind of distribution function. For example, molecules, phonons, photons will correspond to the canonical ensemble, electrons to the grand canonical. Now, the numerator that you have here, so e power minus EI by kBt, this is called the Boltzmann distribution. Okay. So, the numerator what we have here is the Boltzmann distribution, and the denominator, the summation of all this across the different energy levels. This is in statistical thermodynamics referred to as the partition function. Sometimes they use the nomenclature Z instead of writing the summation this all the time, they replace this entire denominator with the nomenclature Z, which is called the partition function, which is the summation of the distributions across the different energy levels. So, based on this distribution function, now we will go ahead and derive the individual distribution functions for each energy carrier. So, for example, molecules, in the case of molecules, what will happen to the energy? They are not discrete, they are continuous, and if you are considering only a monoatomic gas molecule, so only translational kinetic energy is there. In 3 dimensions you have 3 degrees of freedom, half m v x square plus v y square plus v z square. So, we can therefore substitute for energy in terms of the translational kinetic energy, and then we can calculate what is the distribution probability distribution function for molecules. Similarly, for phonons we can substitute the corresponding value of EI. What will be the EI for phonons? H nu into n plus half vibrational energy levels. Okay. And if you look at electrons, So, we can also again substitute the corresponding value of EI. So, all this we will do in the next 2 or 3 classes, starting from molecules. So, and once you derive them for apply them for molecules, they get the name Maxwell Boltzmann distribution. Similarly, for phonons and photons, they become the Bose-Einstein distribution function, and electrons they become Fermi-Dirac. So, we will derive these distribution functions for the individual energy carriers and look at the nature, how they look and how they collapse. Actually, even though the electron distribution function looks quite different from the phonon distribution function, they can actually collapse at some certain conditions, and they will be looking similar. They will become collapse to a Boltzmann distribution function. So, we will see at what particular values they can do that. Then from these distribution functions, so the first part is achieved. We know how the particles are distributed. The next step is to therefore calculate the macroscale properties. So, we are interested in internal energy. So, how do we do that? So, we know the distribution function, we have these corresponding values of energy, we have to take a cumulative. So, therefore, we have to find the ensemble, statistical ensemble of number of particles occupying each energy level based on this distribution function, from which we aggregate everything and calculate the total internal energy. And once you know the internal energy, we can calculate the heat capacity, right. So, from there we should be able to now understand how the microstates are now transitioning and we get the macroscale properties. So, in the next I think 1 or 2 classes we should finish the distribution followed by calculating the internal energy. So, about 2 to 3 classes totally we should be able to complete this exercise, and then we will be knowing at equilibrium systems how these particles are distributed, what kind of energies they possess and what is the contribution and so on. So, then we will go on to cases of non-equilibrium, that is the transport of heat. Okay. So, we will stop here